answers to 1.1. It's the moles review section. We went over a few of these in class, so I'm going to run through the first page pretty quickly. We measure volume units. Okay, volume is measured in liters typically, and it may be measured in milliliters. You can use other, obviously, metric units like microliters and so on, but I'm going to keep to the ones that are most common in a chemistry class. Equally with mass, the most common units we're going to be thinking about for mass are grams and kilograms. Sometimes we may dip into micrograms. We're going to see where the semester takes us. For the amount of particles, okay, well, there's only one good answer for that, and that is the mole. A mole just tells us how many particles we have, and it's usually about a handful if we're talking about something like a molecule. All right, concentration of a solution. Okay, so that is abbreviated with capital M, which is shorthand, really, for the idea of a mole per liter. These aren't different units, they're actually equivalent, and you can really choose which one you prefer. For density, that's a measure of how much something weighs for the amount of space it takes up, or rather how much mass it has for the amount of space it takes up, if you want to be technical. And so for density, we usually are going to be measuring in grams per milliliter or kilograms per liter. And lastly, molar mass. Okay, molar mass tells us how much mass a mole of something has, and that's in grams per mole. All right. Moving on, we've got a volume term here. Okay, we've got to define these terms. So volume. So if you weren't in class, if your name is Mac or if your name is Maya, we tried to define these in sort of everyday language and try and get rid of as much technical jargon as possible. So a few of these definitions may be in simple English, maybe simpler than you might see them otherwise. So to define volume, well, we said it is just the amount of space that something takes up. And that's it. That's volume, just the amount of space. And that's measured in liters or milliliters. All right. Mass is a little bit more difficult to define. It's how much stuff you have. But because we're in chemistry class, not physics, we can actually ignore some of the more technical definitions of mass having to do with inertia, and we can simplify it to thinking that this is really the measure of how much stuff weighs. And this is technically not true. So I'm actually going to put a little asterisk here because there's a technical definition if you've taken physics that differs the difference between weight and mass. But that might be a little detailed for us. All right, a mole. Okay, so there's two things I think we want to know about a mole. One is that it's 6.02 times 10 to the 23 things. It's just an amount of things. It's an amount. And it's usually about a handful, which is kind of the idea behind a mole. It's trying to take a certain number of molecules and then scale them up to something we can deal with. So it's usually about a handful. And that is only true for molecules and atoms. If you want to know what a mole of Timbits looks like, it is not going to fit in your hand. All right. Concentration is a term that talks about, right, in class we actually went into more detail about really what I wanted with concentration. I could have been a little bit more clear with my request. We really want to talk about concentration in solutions. And this is a measure of how much solute or dissolved stuff you have is in a solution. So more concentrated, more solute. Okay. On to density. Density is a measure of mass per unit volume. So if you have a given volume of a substance, how much does it weigh? A more dense substance will weigh more. Molar mass is the amount that a mole of something weighs. Pretty simple. And lastly, we have molarity. And molarity is a measure of concentration in solutions. And I might actually also say molarity is measured in capital M, or moles per liter. Molar mass is measured in grams per mole. Density is usually measured in grams per mil, or whatever, kilograms per liter. I guess it could be other things as well. Concentration is also, for our purposes, molarity, moles per liter. A mole is just a number of things, so it doesn't really have units, or if it does have units, it's units of moles. Mass is measured in grams or kilograms. Okay, so I went through that kind of quickly, so we'll move on. So we've got some questions here. Again, we did some examples in class. I'm going to run through these a little bit more quickly. Also, I am a little pressed for time as far as how long I have this document camera for, so I'm going to go a little bit more quickly than I would like to normally. All right, question is, how many water molecules are there in 3.4 moles of water? Well, I like to say, okay, well, what's given? I know that I have 3.4 moles of water. That's given. And I'll use pink to indicate what I want to know. I want to know how many water molecules. Okay. Well, what I like to do is start with the thing I am given that's specific to the question. And I know that we talked about 3.4 moles of water. And I can picture a mole of water. It's about 18 milliliters. And then I want to say, okay, well, how many water molecules are there in that? So really, I want to turn moles into a number of molecules. And to do that, I'm going to use a conversion factor. And the conversion factor that's going to help here is the mole. So I'm going to say, okay, well, I know that 1 mole is equal to 6.022 times 10 to the 23 molecules. And I want to set it up so the moles cancel out diagonally. So I'm going to have a 1 mole down here, and that's equivalent to 6.02 times 10 to the 23 molecules. I'm going to abbreviate that molec. Moles cancel diagonally, and that gives us a value, with a pick up a calculator, 3.4 times 6.02 times 23. That gives us a value of, if I round that to 2 sig figs, that gives us 2.0 times 10 to 24 molecules. Okay, moving on. Again, we have how many moles of magnesium are in an aerosolized cloud of 4.5 times 10 to the 20 magnesium ions. Okay, so some stuff we don't necessarily need to know. The aerosolized cloud, we won't let that distract us. We're given, we have 4.5 times 10 to the 20 magnesium atoms, and we're asked how many moles this time of magnesium. Okay. Again, we like to start with the thing that we're given, that is specific to the question. You can also argue that we're given a mole, and the molar ratio, but that's not specific to this question about magnesium. We want to start with the one that is specific to our question. So I'm going to say magnesium atoms, and I want to use my molar conversion again to change from atoms or particles to moles this time. And so in the last ratio, I set up the conversion factor so that the 6.02 times 10 to the 23 Avogadro's number was on top. And I chose that because I wanted moles to cancel out. But here I want the number of atoms to cancel out. So actually I'm going to put it down here, 6.02 times 10 to the 23 atoms. And 1 mole lives up top. And I'm going to cancel these out diagonally, like so. Okay. And so here, because the value's on the bottom, we're going to do division. Now, This gave some people trouble in class yesterday. The division using scientific notation can run you into a bit of trouble here. So I'm going to say error on the side of brackets. So I'm going to type mine in, 4.5. And I'm using the EXP button on my calculator, but your calculator may have slightly different appearance for this button. Oh, this calculator also. The light's a little bright there. It's hard to resolve. But it has the same EXP, so this is a bad example. But you might have a calculator and it just has 2 E's. But there's a button on your calculator, chances are pretty good, that does this. This little E in the calculator stands for 10 times 10 to the power of. So if I want to write 4.5 times 10 to the 20, I just say 4.5 E20. And that's that value. I'm going to divide it by 6.02 times 10 to the 23. Now, I actually don't need brackets for this, but I'm going to put brackets in because if your calculator is a little different, I can guarantee that putting brackets here might help you get the right answer. And here we have the number of moles, which is not that many. It is, so if I round to 2 decimal places, I get 7.5 times 10 to the negative 4 moles. Okay. So we'll move on. Question 3. We're talking about a buckyball, and we have 60 carbon atoms in a buckyball, and we have 1,000 buckyballs. So what's specific to our particular question here? Specific is 1,000 buckyballs. This is a property of buckyballs, but it doesn't really have anything to do with the amount we have, and so that might come later. We're going to start with that. 1,000 buckyballs. And I know that I can convert buckyballs into carbon atoms because one buckyball contains 60 carbon atoms. Okay. However, I wasn't quite asked for the number of atoms. I was asked for the number of moles of carbon. So to go a little further, I would need to turn atoms into moles, which is actually kind of similar to the conversion I did here. I'm going to place atoms down here, in which 6.02 times 10 to the 23 atoms, and that converts it into moles. And again, we're going to cross things out diagonally. Buckyballs cancel out, and atoms cancel out. And we get that we have, 1,000 times 60, that's some number, 60,000, okay. Multiplying the tops across. I could multiply by 1, but that would be a bit of a waste of time. And I divide by any of the numbers on the bottom, so I'm going to divide by 6.02 times 10 to the power of 23. And I get, so 9.96677 times 10 to the negative 23. Now, if I want to be fussy here, I would argue that I really only have 1 sig fig's worth of data, because that 6 is the only significant, and there's 1. Both of them are really only 1 sig fig values. And so I really need to round that to 1 sig fig. Okay. So if I round that to 1, this actually gets a little tricky. It becomes 1 times 10, but it's not times 10 to the 20. It's actually 1 higher than that. It's 10 to the negative 19, which is a little bit higher, a little bit larger than 10 to the negative 20. 10 to the negative 19 watts, 10 to the negative 19 moles. So not very many moles, which makes sense because 1,000 buckyballs is a tremendously small number of carbon atoms. All right, moving on. So we've got Liam, and he's aiming to make some fireworks using TNT. And we're to ask, if he needs 5.43 moles of TNT, how many molecules is that? Okay, we're going to start with the thing we're given, which is 5.43 moles. And then we'll just see where that takes us. 5.43 moles. And what do I want? I want the number of molecules. All right, so I'm going to, again, use the mole to do that. 1 mole, I put it down here to cancel diagonally, over 6.02 times 10 to the 23 molecules. I'm going to abbreviate that molec. So these moles cancel out, and this is actually really simple multiplication here. 5.43 times 6.02, 523, and I get, well, how many sig figs should I get here? 3. So I'm going to say 3.27 times 10 to the 24, and the leftover units that didn't cancel out were molecules. And there we go. Now, how many carbon atoms is that? Really? That's what this question asks. Okay, well, I know how many molecules of TNT we have here. And I can see that the molar ratio is that there are 7 carbon atoms for every atom of TNT, or pardon me, for every molecule of TNT. So if I've got this many molecules, a lot of molecules, each one of those has 7 carbons. So I could just reason that through, or actually I can do a conversion, which I'm going to do, because I think a lot of things can be written as conversions, and I like to do it if I can. So 3.27 times 10 to the 24 molecules. I'm going to say for one molecule, that converts to 7 carbon atoms. So the molecules cancel out, and I can see now that it's just a simple multiplication. So I still have that value in my calculator. I'll just multiply by 7, and I get 2.29, is how that rounds, times 10 to the 25. And that's atoms of carbon, if I want to be specific. Okay, great. Next, okay, candle is made of 5.68 times 10 to the 25. Wax molecules, and we want to know how many moles. Okay, so again, we're starting with some value, some number of molecules, 5.68 times 10 to the 25 molecules. And we're going to convert that to moles. Okay, so I know that I need molecules on the bottom. 0.2 times 10 to the 23 molecules. I'm going to again abbreviate that molec because I didn't leave myself enough room. And well, that's 1 mole, right? Okay, so molecules cancel out, and I have this division again. So if you had trouble with the example in class, this is a good one to work the kinks out on your calculator with. All right, so we got 5.68 to the power of 25 divided by 6.02 to the power of 23. Oops. 23. There we go. And it turns out to be 94.4 moles. 94.4 moles. Which is a deal-with-able amount of moles. That's probably a pretty big candle, though. All right, and lastly, we got Gucci Mane. He's got a Bart Simpson necklace that contains 20.5 moles of diamonds. That's true. That's one of my favorite rapper necklaces. All right, and the question is, how many carbon atoms does he require to make that necklace? Okay, a lot of unnecessary information. But lastly, we do write the answer using scientific notation and an expanded form, which is a good habit to do every now and then to remind ourselves that these big scientific notation values are not just a little big, they're really tremendously big. It's like a lot of atoms, probably. All right, so we're going to start here, 20.5 moles. We'll convert that into molecules. Okay, so I got to say, okay, I need moles to cancel out, so I'm going to use 1 mole here. And on the top is a 6.022. Oops, I forgot. We should probably only use 3 sig figs just for consistency's sake. But the 4th digit is actually a 2. Times 10 to the 23 atoms. Diamonds are really just carbon, right? Okay, good. That's just a simple multiplication. So in Gucci Mane's necklace, we've got 1.2, how many does sig figs? 3 sig figs. 1.23 times 10 to the 25 carbon atoms. And we're going to write that in expanded form, which means we're going to move this decimal place over 25 times. So first I'll write this 1, 2, 3. So let's move it over twice. And I need another 23 zeros to get all the way down to the decimal. So I've got to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And if I want that value to just seem like more than a string of zeros, I could actually put a comma every 3, and that helps me orient myself a little bit. It's still a little bit, starts to lose meaning for me after the, I would say, 9 zeros. I start to lose the idea about how big it is. I just know it's big. But that helps a little. All right. Moving on. Last page of 1.1. Okay, what do we got here? The molar mass of uranium pentafluoride. Okay, we did this in class. We had to first decide uranium pentafluoride looks like this. Okay, and why is that useful? Well, because in order to find the molar mass, we need to know what atoms compose a single molecule. In this case, a uranium and a fluorine. So I might take a second and say, okay, well, what about uranium? What's the molar mass of uranium? So I look at my periodic table. I'd say, okay, excuse me, I got the hiccup, sorry. Molar mass of uranium, 238.0. Okay, 238.0. 0.0 what? Okay, well, if you're talking about a single atom, it's a Dalton or an AMU, but we're concerned about the molar mass. So that is also the same thing as a number of grams for a mole. Okay. And for fluorine, I look on the periodic table and I find it's 19.0 grams per mole. And when I add those together, and of course I add 5 fluorines. So I'd say, okay, that's 238 plus 5 19s. And I get 333. 333 grams per mole. I'm playing a little fast and loose with the sig figs there. Technically, that should be 333.0 grams per mole. You know what? Actually, why don't I just write it that way? That makes sense. 333.0 grams per mole. But like I've said earlier, I don't really want you getting too distracted with sig figs right now. I really want you to concentrate on conversions. All right. Okay. Protocol requires us to measure out 0.3 moles of calcium hydroxide. How much should we weigh out? Okay, I think you can hunt through the periodic table yourself and decide on how much the molar mass is here. So I'm going to do it a little quickly. So calcium's 40.1. There's 2 oxygens, so that's 32. 2 hydrogens is 2. Okay, so that's 72.1, 74.1. 74.1 grams per mole. Okay, if we want to turn moles into something else, we just start with the moles. All right, and I'm going to multiply it by a conversion factor because I need to turn it into, well, we're asked how much should we weigh out? Okay, so that is a question really. Weigh. What do we weigh on a scale? We weigh mass. So we need to convert moles to mass. And so to do that, we're going to use the molar mass. That is a conversion factor that converts between them. Now I want moles to cancel out, so I'm going to put the moles on the bottom. 1 mole. And for a mole of calcium hydroxide, I get 74.1 grams. All right, so the moles cancel out diagonally nicely, and I just have a very simple calculation. 0.3 times 74.1. Oh, that doesn't look good at all. Insert times 2.223, but actually if you notice there's only 1 sig fig, so that's actually just the number 2 grams. We weigh out 2 grams if we want to make that concentration, or pardon me, if we want to have that many moles of calcium hydroxide. Again, okay, we've got Logan's got a steel ring, it's 4.95 grams. All right, and we want to know how many atoms of iron are in Logan's ring, so we need to convert grams into atoms. So I'm going to start with the grams, 4.95 grams. Okay, and somehow I need to turn it into atoms, but I don't have a grams to atoms conversion because different substances have different densities. However, you probably remember that if you want to do a conversion and you're not sure what you should start by trying to turn things into moles. So that's what we'll start with. Okay, so I've got 4.95 grams, and I can turn that into moles. I can do that using the molar mass of iron. The molar mass of iron is 55.8 grams for every mole. So I can say, okay, well, I can multiply my 4.95 grams. I want the grams to cancel out, so I'm going to put my grams down here because I want to turn this into moles. And that's for every 1 mole. So 1 mole lives up here. Okay. And that's not quite what I was looking for. I wanted the number of atoms, so I still need to go one step further to turn moles into atoms. And that's something we can do using Avogadro's number. That's a conversion factor as well. It turns moles. So 1 mole. And what's a mole? Well, a mole is a certain number of atoms. It's 6.02 times 10 to the 23 atoms. And then moles cancel out, grams cancel out. I always get a certain sense of happiness deep down when I cancel out all my units like that, and I get some number of atoms of iron at the end. How many atoms do I get? You ask. I get 4.95 times 1 times 6.02 times, oops, don't want to do that, exponent 23. And that's all divided by 55.8. And when I do that, I get 5.34 times 10 to the 22. And I get 3 sig figs here from the 3 sig figs there, and 3 sig figs for my molar mass. 5.34 times 10 to the 22. Okay. Atoms of iron. And that's how many atoms it takes to make Logan's ring. Okay, moving on. The molar mass of glucose, I'm going to rush through this. 6 12s, so I know carbon is 12, molar mass, so 6 12s is 72. Hydrogen, that's 12. Oxygen, 96. Okay, so I just add those together, really. And I'm getting these numbers, of course, by saying, okay, oxygen has a molar mass of 16, and there are 6 of them, so I multiply 16 by 6. And I've done that calculation enough by now that I'm comfortable saying that I think that's 96. And that's what I did with these numbers. I know hydrogen is 1. If you do enough organic chemistry, you kind of memorize these pretty comfortably, and you do that multiplication enough. Anyways, moving on. So what does that give us? That gives us 96 plus 72 plus 12. I don't want to screw this up, so I am actually going to revert to my calculator at this stage, I want to move quickly. So 180 grams per mole is the molar mass. What does this question ask? What's the weight of 1 mole? Well, the weight of 1 mole is 180 grams. They're very slightly different questions, so we need to answer very slightly differently. What was really the intention with this question is to point out that these are similar questions, despite the fact that they might look like they're asking for different things. In fact, they are, but not very different things. Okay, let's move on. Let's talk about gold bar. Okay, we have a 12.4 kilogram gold bar, and we want to know, okay, how many moles are there? Sure, okay, fine. So we could start, so you might have converted that directly to grams in your head. Bully for you. I'm going to do the long route. I'm just going to say, okay, well, my conversions for everything else are the same as my conversions for metric. So I want to go from kilograms, so I know 1 kilogram. It's the same as 1,000 grams. My kilograms cancel out, great. Now, I still don't have the number of moles, but I know that gold has a molar mass of 197 grams per mole. Okay, so that number I can use to turn these grams into the moles I'm looking for. So I want grams to cancel out over here diagonally, and that's the rule, so 197 grams. Oh, I shouldn't round it, actually it's 197.0. Let's cross that out. Looks a little messy, apologize. Looks really messy, actually. And there's 1 mole over here. Grams cancel out as well, leaving us with moles. Okay. So I say I multiply 12.4 by 1,000. That turns things into grams. And then I divide it by 197. I don't need to put the 0.0, but I can. And then we get 62.9 moles of gold. Done. All right, moving on. We got Saiba. She's making some soap. We have 0.45 moles of stearic acid, which is a pretty common fat. And then we want to know how much you should weigh out. So that means mass. So we need to turn this into a mass. Okay, which is kind of the opposite of what we just did here. So let's see if we can work this out. So we're going to start again with the thing we have specifically. So we've got 0.45 moles. And we need to turn that into grams. Okay. So I need to know the molar mass of stearic acid. Well, that's kind of a pain. Okay, I'm going to try and do it quickly, though. So I have 18 carbons. That's 18 times the molar mass of 12.0. 216. 36 hydrogens. Hydrogen has a molar mass of 1, so that's 36 in total. And then 2 16s for 2 oxygens is 32. So if I add those together, 216 plus 36 plus 32, that's the sort of math I'm liable to make a stupid mistake on, so I want to make sure I use my calculator for it. Okay, it's 284. 284 watts? Well, 284 grams per mole. All right. So if I want to turn the number of moles of this protocol into a number of grams that Saiba can weigh out, I want my moles to cancel out. So 1 mole of stearic acid is able to be converted into 284 grams of stearic acid. Moles cancel out, and I can take this number 284, multiply it by 0.45, which is a little out of order, and then I get 127.8. 127.8 grams. Now, I only had 2 sig figs here, so actually I'm going to round that in kind of a funny way. That's 130, but if I put 130, that's sometimes some ambiguous amount of precision. So I like to write it in scientific notation, 1.3 times 10 to the 2 grams. That shows me that we don't know any more precision than that. It's around 130, give or take. Maybe it's 135 or 125, not that certain. If I say it's 130, it implies that I know to a higher degree of precision. All right. Last 2 questions. So we want to know how many carbon dioxide molecules are there in a 0.700 gram block of ice. Dry ice, that is. Dry ice is just solid carbon dioxide, frozen carbon dioxide. All right, let's find out. So we got to start with whatever we have. We have 0 grams of carbon dioxide. Okay, and then we're going to set up a conversion factor. So what do we want? We are asked for molecules. Again, I don't have a grams to molecules conversion. I don't think one really could exist. However, if we're ever not sure about what to convert things to, we should probably convert things to moles. And maybe things will reveal themselves, a path for ourselves, because we want molecules at the end. Okay, so I can convert grams to moles. I can do that using molar mass. So that's, I just add up these. So that's 12, 32. That gives us a molar mass of 44.0 grams per mole. Okay, and that tells me that all my grams cancel out, so I'm actually going to put them down here, 44.0 grams. That's for 1 mole. And so our grams cancel diagonally. Oh, but we don't want moles, we want molecules. I almost went a little too quick there. So to turn moles into molecules, I do know how to do that. That's Avogadro's number. That says, okay, well, that's I have 1 mole. Then I have 6.02 times 10 to the 23 things, in this case molecules. But that thing can change. It could be atoms or it could be particles, depending on the question. Okay, and now we have molecules, which is what we wanted. All right, so I'm going to do that multiplication nice and quickly. 0.7, I don't even really need to put 0.700 because there's lots of zeros over here as far as the calculator is concerned. Times that 1 times 6.02 times 10 to the 23. And then I'm going to divide it by 44. I get, how many sig figs should I be allowed? 3. So it's 9.58 times 10 to the 21. molecules. Last question. A cloud is composed of 3.5 times 10 to the 35 water molecules. Okay, and the question is, well, how much does the cloud weigh? And again, weigh is a word. We want to see that and think mass. That's what that means. Okay, we're looking to turn things, and if that isn't clear even, we say, okay, mass, I can think grams. That's something I can weigh out. I measure things in grams. Again, I start with the thing I know, 3.5 times 10 to the 35 molecules. It's important to include the units. And I say, okay. I don't know how to turn it into mass, but I do know how to turn it into moles. But to do that, I need the molar mass. Molar mass of what? Of water, H2O. There's a molar mass of 2 hydrogens, that's 2, plus an oxygen is 6, that's 18.0 grams per mole. All right, so, oh wait, that's not what I want to do. I want the molar mass later, but right now I need to turn that into moles, so I actually need Avogadro's number for that, 6.02 times 10 to the 23 molecules, and that's for every 1 mole. Now I can use my conversion factor of molar mass. Molar mass of 18.0 grams for every 1 mole. Molecules. Okay, so I have 3.5 times 10 to the 35 times it by 18. 3.5 times 10 to the 35 times 18.0 technically, and then divided by 6.02. Oops, nope, not that. 6.02 to the power 23. All right, and we have 2 sig figs for our answer, so that should be 1.0 times 10 to the 13 grams. That sounds like an awful lot of grams to me. When I have a really big number like that, I like to try and contextualize it. I might say, okay, well, how many kilograms is that? Well, I can drop this off by 3 tens, divided by 10 3 times. I can get a number of kilograms. Okay, that's still big. Let's see if we can figure out exactly how big. Okay, so I'm going to write that out. So it's 1 and 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, kilograms. And I'll put some commas in. So that's 10 billion kilograms. That sounds like a lot. In fact, that sounds like so much that my first intuition is that I must have made a mistake when writing this, because that sounds too big for my intuition. I don't think that 10 billion kilograms is how much water molecules weigh. Pardon me, how much a cloud weighs. But I'll need to do some thinking on that, because sometimes intuitions can be wrong. All right, that's the first assignment. I'm going to do the second one over the weekend, and I'll get it up to you guys as soon as possible. Happy studying.